Okay, guys, today we're going to be talking about proportional relationships. And most of what we have explored so far has had to do with part to whole relationships. And we might say 3 out of 4 pieces were shaded. We might also say 3 to 4, or we might say 3 semicolon 4. All of those are proportions and proportional relationships. And we have been using those proportional relationships to establish a pattern and then find missing information. So we have 3 is to 4 as x is to 8. And what we've been doing is using a cross multiply and divide strategy. 3 times 8 is 24, divided by 4 is 6, to find the missing fraction or part of fraction. We've also been using 3 is to 4 as x is to 8, and using the giant 1 strategy. 4 times 2 is 8, so 3 times 2 is 6. You notice in both cases we get the correct answer. What we're going to be doing is playing these proportional relationships out a little bit further, and as a result, when we graph them, they're going to make something very specific and unique. And to review what we already know about proportional relationships, we know in proportional relationships there is a constant rate of change that is the same each time. And that when you graph this out, this constant rate of change means it's going to be a line, a straight line. And the other condition of being a proportion or proportional is that it has a starting value equal to 0, meaning that when x equals 0, y equals 0. In other words, this line that we established goes through the origin. And so it becomes important that as we explore these relationships, that we take a close look at how to identify a proportional relationship in a table. So let's start with x and y. X and y, and we have 0, 0, 1, 3, 2, 6, 3, 9. And if we were to write these as fractions, 1 over 3, 2 over 6, 3 over 9, we would identify that they are all equivalent fractions. But what we're really concerned at as we look at this is we are concerned about the conditions of proportionality. One, is there a constant rate of change? To find out if there is a constant rate of change, you must identify the delta y. The delta y in this case happens to be 3. In each case, 3, 3. So your delta y is 3, 3, 3. And your delta x is 1 each time. 1, 1. So my delta y over my delta x, my rise over run, is actually 3. So my delta y over delta x is 3 over 1, which equals 3, which is constant, the same each time. If the change is constant, you've met the first condition of proportional. The second condition is that it must go through 0, 0. When x is 0, y must be 0. And if it's 0, 0, it goes through the origin and meets the second condition of being proportional. So from looking at this table, we know the change is constant, 3 over 1, each time, 3 over 1, 3 over 1, 3 over 1. And we know that it goes through 0, 0, and so we would conclude that this graph, or this line, is absolutely, with a certainty, proportional. Now you can see that we have a graph where we have properly scaled each side. We're counting by 1s on the x-axis and 3s by the y-axis, and we've graphed these points. We have 1, 3, 2, 6, 3, 9, and you'll see that they form a straight line, and that straight line goes through the origin 0, 0. So from looking at the graph, we can see that our run, or our delta x, is 1. And we're going to code that in green. And our rise, our delta y, is 3. And we're going to code that in pink. And when we have slope, our slope of the line, or our steepness of the line, is actually our delta y over delta x, which is actually our rise over our run, which actually becomes 3 over 1. And then when we look at this line to determine whether or not it is proportional, we look at where the line crosses the y-axis, and the y is the axis that goes to the sky, and it crosses at 0, 0. In other words, it goes through the origin. So once again, we look at our two conditions. Does it have a constant rate of change? In other words, is it a straight line? Yes, it is. Does it go through the origin? When x is 0, is y 0? Yes, it is. So this relationship, according to our two conditions, is also proportional. And now we're going to use what we know about proportional and what we know about what we've already learned about proportional relationships, and we're going to write an equation for this. And the equation that we have is y equals kx. And k is going to stand for our rate of change. It is also called our constant because the change is constant. It is also called the unit rate. It is also called the slope and the coefficient. In addition to that, it can also be described as your delta y over delta x, which is your rise over your run. And this describes the steepness of the line, what the line looks like over here. So when we write the equation for this line right here, described in this table and in this graph, you would get y equals 3 over 1x, or you might do the division over here and you might write y equals 3x. And now today, we are going to introduce linear relationships. Linear relationships are very similar to proportional relationships in that the rate of change is constant, but they are going to have a different starting value. All proportional relationships are linear relationships, but not all linear relationships are proportional. And we're going to explain why next. So before we launch into linear relationships, I think it's important for us to review what we know about proportional relationships. Number one, the rate of change is constant. In other words, it's the same each time, meaning that you have a straight line. And the second condition is that your starting value equals 0. In other words, when x is 0, y equals 0, and it goes through the origin. These are the two conditions. Your rate of change is constant, and your starting value is 0. And you write this equation like so, y equals kx. Now, when we go into linear relationships, it's going to look a little differently. In linear relationships, your rate of change is constant. But your starting value can be any number. So your starting value can be any number. And our equation looks like this. Y equals mx plus b. And I don't want you to be scared by those differences because they're going to be very similar. And one of the things I want you to realize is that m and k are actually the same thing. M is going to be your rate of change. It's going to be your constant. It's going to be your unit rate. It's going to be your coefficient, which is the number attached to the variable. It's going to be your rise over run, which is going to be your delta y over delta x. And we're going to call this slope. And if you recall, k had all of the same names over here. This is also slope, rate of change, constant, unit rate, coefficient, rise over run, delta y over delta x. It's going to be the same thing. So the thing that's different here is going to be b. And what I want you to recognize is that the b over here is implied. It's implied because there's only one thing you can add here that would also equal k times x, which is 0. So the interesting thing is that the b becomes your starting value when x equals 0, y equals whatever b is, and this is also your y-intercept, so that wherever the line crosses the y-axis, that is what this number is. So let's take a little look at a graph and a table. So let's look at our table. We're going to look at our delta y, which is our change in y. 2 to 5 goes up 3, 5 to 8 goes up 3, 8 to 11 goes up 3. So our delta y is going to be 3 each time. Delta y, 3, 3, 3. And our delta x, change in x, which is this is our delta y is our rise, and delta x is our run. So delta y over delta x is rise over run. And our delta y was 3, and our delta x is 1, 1, 1. So our delta rise over our delta x is rise over run, which equals 3 over 1. And you'll notice that it's the same each time. If it's the same each time, then we know that it's going to be a straight line. However, in this case, when x is 0, y is 2. So it does not go through the origin, which means it is not proportional. So when x is 0, y is 2. So this would not be proportional. And if we graph this, we go over to 0, 2, 1, 5, 2, 8, 3, 11. We get a straight line that looks like so. But the difference here is that while it might be a straight line, the y-intercept, where it crosses the y-axis, happens at the number 2. Now our run is still 1, and our rise is still 3, so our delta y over delta x, our rise over run, is still 3 over 1. So now when we write our equation in the y equals mx plus b format, we get y equals, what's our rise over run? 3 over 1x, plus what's our y-intercept? 2. So our only real change here, and this could be rewritten with doing the division, 3 divided by 1 is 3, y equals 3x plus 2. So you'll see in our equation, you'll see the y-intercepts when the coefficient is 0, or when the y-intercept is 0, and then you'll see your rise and your run. Your rise would be 3, and your run would be 1, and if you divide that all out, you get your slope as 3x. So the only real difference between the proportional relationship and the linear relationship is going to be the origin. Where does the line start? If the line starts at 0, 0, it is a proportional relationship. And all of your points on that line would be equivalent fractions. However, if your line starts or crosses the y-axis somewhere other than 0, it is not a proportional relationship. It is still a linear relationship. And that's the difference between linear and proportional. And you should be able to see now, from looking at all three of these, that your slope, your rise over your run, is the same in all the equations. The only difference between proportional and non-proportional linear relationships is going to be the origin, or where it crosses the y-axis. When x is 0, what is y?